Hi, I'm Daniel, and I'm a machine learning solutions engineer at Google Cloud. In this section, we will learn about LSTMs, a special type of recurrent neural networks that proved really popular in the last couple of years. Let us first recap what sequence models are and how they differ from other structured data problem formulations. Observe these examples. In the first case, the task of predicting the next word in a sequence, and in the second case, the problem of translating, in this case between English and Russian. What do these two language models have in common? Our intuition is that the order of the data, that is the order of the words, is really important. Here is another example of a sequence model problem. You might already be familiar with the Smart Reply feature in Gmail, where based on an incoming email, 3 different short answers are suggested to you. This is another example where the order, in this case the order of sentences, matters. Finally, moving on from written text, in case of speech-to-text transcription, the sequence of uttered sounds also becomes key in successfully parsing the written version of the spoken words. So what could we use to process written or spoken text or any other sequence? It is, in fact, possible to just use classic deep neural networks on text and other sequences as well, but as we will see, recurrent neural networks are usually better suited for the task. Here is a very schematic view of a classic deep feed-forward neural network. The input layer at the bottom reads in the input data, the hidden layers in the middle learn features, and the final output layer is expected to reconstruct the desired output. A few things to notice here for each type of layer. In case of the input, there is no defined order for our input data. Of course, the data vector, or tensor, is passing the input data in a given order, but we could just as well rearrange this order to a different permutation and would end up with an equivalent network. In case of the hidden layers, their inference is stateless, meaning during prediction, they will not change feature values dependent on what they have seen before the current input. Finally, the output layer structure means that there is a fixed output size. One could think of ways to manage this, such as having an output layer of the size of the longest sequence, but this might be impractical. As we just discussed regarding the fixed length output layer, indeed sequences can come in arbitrary lengths, and real language also contains both short and long sentences, such as in this slide. Now, if we try to feed these into our network, in this case including an embedding layer, this would make it possible to aggregate the embeddings into fixed size output vectors, but basically this is still just a bag of words approach, and we still do not make use of the order of the words in a sentence. In real life, however, just as for languages as for many other sequences, the order, the structure can be very important. On the left side, the first sentence means much more than just the bag of words below, and more often than not, this bag of words could spell out multiple grammatically correct, but not necessarily true sentences. Other examples where the structure of the sentence is essential is in the case of humor or sarcasm, which are famously hard to understand in any case with machine learning. That said, for example, if we were only interested in topic understanding, then for such tasks, indeed a ranked list of words or n-grams, which are groups of n words, can be sufficient. Here is an example for our earlier sentence represented as bigrams. This representation does retain slightly more of the structure than pure bag of words. However, while it might be tempting to increase n to create longer and longer n-grams, this would cause an explosion of dimensions and also very sparse values. So let's look into recurrent neural networks, RNNs. The key insight behind RNNs is that why don't we wrap a classic deep neural network in a loop? To understand this view of RNNs, first let's have a look at a simple schematic example. This network has a time-variant input, x, a time-variant output, h, and A is a small neural network with its output h also fed back into it as input. How is this even possible? Well, during training, we will consume the whole sentence through this network with a feedback loop, and we will use the gradients to adjust weights across the whole sequence. Let's look at the same network in a different visualization, unrolled. In this case, we show the neural network A multiple times, but remember that they still share the same weights. Indeed, this idea is the secret sauce of RNNs. The right side might look like a classic deep neural network. However, for each A, they share their weights, and the backpropagation uses gradients for all time points. This logic will allow the RNN to be able to provide temporal context. That is, if a piece of information was shared a few time steps earlier, the hidden state of the network might still be able to use that knowledge to help correctly predict, in this case, the next word. So, if RNNs are so great, do they have any drawbacks? It turns out that the simpler ones do, and let's look into what these are before we introduce a solution to them. There are two main problems with long-term RNNs, and both are related to the gradients and the effect of chaining on them. As the gradients pass through the whole, potentially long sentence, they can be unstable either way, either exploding to very large values or vanishing towards zero. This latter, vanishing gradients, in other words, means that the network can in practice forget relatively fast. Again, while in theory, even the very last time step is influenced by the very first steps, even in a very long sentence, in practice, however, this effect can fade out in many cases, partly for numerical reasons.